What up, guys? Today is SpideyPhysics birthday number 1. It's been a year since I posted a video on this channel, and I wanted to go over, talk about what we've done on this channel, talk about all the physics classes I've taken in my life, put things in a perspective, So I think I started off with Gauss's law. I was doing a class on electricity and magnetism, posted some stuff mainly on electricity. I remember the vector, not the vector, the electric potential was a big thing. But then when we passed halfway through the semester, I got a bit lazy and I did not post much stuff on magnetism. So hopefully I can redo electricity and magnetism sometime in the future. Then I think I did modern physics and optics. So I split this up. First did like a series of videos on optics. Then I did a series of videos on modern physics. Very quickly quantum mechanics, very surface level, nothing super serious. Also some relativity, Einstein. I think the photoelectric effect was in there too. Some stuff like this. Then over the summer, I got a bit lazy as well. I was planning to do a math video series on this channel, but teaching math is a bit strange. I don't know where to start. Like, do I start super easy and talk about numbers like 1, 2, 3, 4, 5, addition, subtraction, or do I jump into functions or calculus? So I think that'll be in the future as well. Then we got into quantum mechanics, which is super cool. But honestly, it is challenging for me. Like, I've studied this class 1 time, 2 time, maybe. Maybe this is the 3rd time. And it is tough. Like, the problems are tough. They're very long. The intuition of it is pretty strange. But I think it is a cool class as well. And I think quantum mechanics is the class that I'm going to spend the most time on this channel. I think the main reason I started this channel was to do like a series of diary sort of vlog videos about what I think about quantum mechanics, so that in the future I could look back at it and be like, oh yeah, I've definitely progressed since then. I think teaching people stuff like this helps you wrap your head around it. If you speak it out on video and you watch it back afterwards, or you talk about it with people, maybe it becomes a bit easier to understand. I think so, at least. So anyway, that is a summary of the channel so far. Hopefully next year it's going to get better. Consistency is going to get better. Who knows? We'll see. But I wanted to talk about, as like a little bit of a cool birthday present to the channel, all of the physics classes I've taken. So I'll start off. Normally a physics curriculum is like taught with respect to history. So you start with classical mechanics, which is Newton, which is probably the first physics that you start with. This guy was living around the 1600s. So 1600s was the first kind of blossoming of physics, classical mechanics. This is equations of motion. You throw a ball in the air, calculate where it falls, how long it falls, the path of motion it takes. This is also related to planetary motion. So the planets move around each other in ellipses or other conical section type functions. And yeah, not just Newton, Kepler worked on this stuff. Mr. Galileo, he started off pretty big with classical mechanics. But anyway, I'm not going to talk about the people or the history. I've taken classical mechanics maybe, let's see, I started off in SageUp, first introduction to classical mechanics. I think it was just called mechanics. This is where you do problems like you have a wedge or an inclined plane and a block and it's sliding down. No friction or add friction. How much does the block weigh? How fast does it accelerate? Stuff like this. I remember pendulums. We did a lot of problems on pendulums. Let's see, what else? I remember this problem with pulleys. So imagine a table with 2 pulleys at the edges of the table and a rope going over the pulleys, and the rope hangs over the edges of the table. Then there's a block of mass 1 over here, a block of mass 2, and then the ropes over here on the table attached to a 3rd block, and it's asking you, how does the system move around, which way does it accelerate, stuff like this. So in classical mechanics, you learn about a lot of differential calculus. You got to take derivatives, because to find position, well, you can find position, then you can take a derivative of this with respect to time and get velocity, and then do that again and get acceleration of the system. Gravity, pretty important. That is a form of acceleration. But some of the math that you learn is just algebra, a lot of substitution, calculus. and free body diagrams and a bit of vectors. Vectors are important when it comes to classical mechanics. So that's the first class. I took this once in college, then I took it once in university. And in university, you have the first classical mechanics course, and then you have advanced classical mechanics, which talks about other ways of finding the equations of motion. So not just Newton, we got Lagrange, we got Hamilton. Let me see how to word this here. I think Newton's laws are snapshot type equations. So let's say I throw a ball and then I stop time, or I take a picture of the scenario. If I know the forces acting on this ball, right? Newton's second law says F equals ma. I can know the mass, I can know the force on this object, and I can find the acceleration. So it's kind of a snapshot, instantaneous type of problem-solving system. With Lagrangian mechanics, which you learn in advanced classical mechanics, you more look at the energy of the system, or you look at the whole picture. So not just when I throw the ball and take a snapshot, it's me throwing the ball from time equals 0. Like I throw the ball moves, falls, and then the whole system stops. If you look at the whole movie of that, Lagrangian mechanics kind of uses this principle, or principle of least action. So he says the equations of motion follow a path that minimizes the action, and the action is this thing that's like energy times time or something like this. You may see this on coffee cups. It's like physics is lazy, or the universe is lazy because it takes the path of least action all the time, which is pretty interesting. So it's like two different methods of getting to the same thing, which is the equations of motion. So that is advanced classical mechanics. You also maybe look at some more complicated things like more complex planetary motion, but I can't really remember that too much. Maybe that's going to be in the future. So that is classical mechanics, one of the big fields of physics. Then we got electricity and magnetism, of course. Normally, you learn E&M in college, very quick course. It's like half the semester is on electricity, maybe a few weeks on electronics, circuits, resistors, stuff like this, which I don't think I've done any videos on here, not in detail. And then the second half of the semester is magnetism. And then you also do a little bit of AC circuits. So you have DC circuits and AC circuits and electricity and magnetism. Normally those four things are placed together in one semester, which is a lot. But in university, they split it up into a whole semester on electricity. Here you do a lot of calculus. The electric field is a vector field, so you do a lot of vector calculus. And you basically just try to figure out how to get Maxwell's equations, which are four equations that describe the motion of the electromagnetic field. There's some other equations there too, but that's pretty much it. E&M is really cool. One of my favorite things. I like it much more than classical mechanics because it talks about like an invisible force field. It's kind of like Star Wars. So they have electricity in one semester, magnetism in another semester, and magnetism is very, very strange. Much more strange than the electric field. That's why they do it like this. First, you learn the electric field. It's a bit more simple, maybe. Then the magnetic field curls around and does all this crazy shit. So magnetic field is the second semester. Also a lot of vector calculus. So along the pathway of learning physics, you got to learn a lot of math as well. And then you have also another course on just electronics. So you learn binary, how to basically binary language. So computers read ones and zeros. How ones and zeros are implemented in a computer is if there's a current running or there's no current running, or if a voltage is between a specific region. So let's say, I don't know, I have 2 points here. If the voltage between these 2 points is 0 volts or very close to 0, 0.1 volts, something like this, that is considered a 0. But if the voltage rises to, let's say, above 3 volts, it could be 3 volts, 3.5, 4 volts, that is considered a 1. And if you change the voltage like this, depending on your circuit, you can basically create a language for computers to understand zeros and ones. With this binary language, you can create logic gates, which is like a collection of zeros and ones go together, they spit out some other answer. And from logic gates, you can basically create thinking machines, and that is very cool because it's very modern. Electricity and magnetism was first finalized. I mean, discovered and finalized around the 1800s, I would say 1800s. So classical mechanics, 1600s, E&M, 1800s, maybe 17 to 1800s. Lots of chemistry happening there too. And electronics became big in the last century, 1900s. You know, first computers came out like around World War II, right? 1940 or something like this, 1950. And then there was an explosion of the internet in the 2000s. So super crazy course. Electronics on its own can be an entire degree, electrical engineering. So we have the realm or the reign of E&M. Then we have thermodynamics, which is awesome because thermodynamics links everything you can ever think of together. It links together chemistry with classical mechanics, E&M, any kind of engineering, any kind of literally anything, bro. Like biology, thermodynamics is connected to everything. You can boil down absolutely anything you can think of or talk about to thermodynamics. That's all I'm going to say for that one. Pressure, temperature, PV equals nRT. Maybe that's a bit more chemistry, but thermodynamics goes hard. Oh, there's a few laws of thermodynamics. So let's see. One is about entropy. The entropy in a closed system always increases, or something like this. So the universe itself, if it's a closed system, which we think it is, its entropy always increases, which means disorder always increases. Lots of things we could talk about here, but I'm not going to talk about it right now. It's going to make the video immense. But maybe we could do a thermodynamics course on this channel in the future. Maybe. That would be cool. So one is that. Another law of thermodynamics is heat flows from specific bodies. So from a cold body, heat leaves. From a hot body, heat leaves as well. I don't know. Cold bodies accept heat, right? Because cold bodies get hotter. Like if you leave a beer out on the countertop, it's going to get hotter. If you leave a hot, sunny side up egg, it's going to get cooler. So that is, I think, the first law of thermodynamics. The second is the one on about entropy. And then the zeroth law, there's a zeroth law that was so fundamental they named it the zeroth law. I don't know what that one is. We're going to move on from thermodynamics. So we got classical mechanics, E&M, thermodynamics. After those guys, I think you can get to the heavy hitters, which is quantum mechanics, which we're doing a series about right now. It's very, very, very interesting subject. And it was literally birthed from the 1900s onwards. In the year 1900, Mr. Max Planck published a paper, I think, where he introduces the Planck constant. A few years later, I think in 1904, 1905, Einstein came in and he's like, this Planck constant can actually help with the photoelectric effect, which is, I think, the first, maybe Planck's papers were the first examples of quantum mechanics, because what he was looking at is the radiation law, which is like, you know, when people making swords, they put the sword, the piece of metal, in like a hot fire, and then the sword starts glowing. They saw that at different temperatures, the glowing light is a different color. So this is the radiation law. Depending on the temperature, the light emitted from that object is different. So you can put temperature on the x-axis and wavelength of light on the y-axis, and you can get an interesting looking graph. Planck was trying to figure out what the mathematical formula of this graph was, and he was like, there's no way of doing it unless we introduce this constant, the Planck constant. So I think that is the first sort of subtle discussion of quantum mechanics. And then Einstein was like, yo, if you beam light at a piece of metal, it shoots off electrons. This does not depend on the intensity of the light. It depends on the frequency of the light. There is a cutoff frequency, stuff like this. Maybe we'll talk about that in depth as well. And then in 1910 to 1930, around 1927, was the big quantum revolution, big heavy hitters. They were trying to answer questions like, okay, if we model an atom, right? Because people back in the day didn't believe in atoms. Then they started figuring them out, like the gold foil experiment. You have a piece of gold foil and you're shooting electrons or alpha particles off of it, and the alpha particles ricochet and some of them pass through. You figure out that there's like, you know, the gold foil is made out of these atoms. And then there's this Millikan oil drop experiment that makes you figure out that there's an electron in the business. So people start figuring out matter is made up of smaller things. And then they were like, okay, let's say there's a nucleus, right? Protons and neutrons, or maybe just a proton, and then an electron kind of zooming around it like this. The planetary model. They tried to model it like the sun is. My bad, guys. My dog started barking, and then the sun set. We were on the planetary model of the atoms. You know, if the electron is moving like this, people thought that it would spiral into the center of the nucleus and explode because of energy conservation or something like this. So they were like, how do we figure out what the electron is actually doing? In order to figure that out, we got to create a new theory called the theory of quantum mechanics, super small things. And that was like completely revolutionary because people back in, I don't know, late 1800s, they were like, yo, we figured out so much shit that basically all of physics is figured out. All we need to do is fine tune some things, look for details in the sixth significant figure. So like after the decimal point, 6 digits after that. But then Mr. Planck and Mr. Einstein and all the guys that figured out quantum mechanics threw a wrench in the business. And also, shortly after that, Einstein dropped the theory of relativity and the general theory of relativity, which is another subject. So, in summary, classical mechanics, electricity and magnetism, also electronics in there, thermodynamics, quantum mechanics, and then we got relativity, which is the study of things that are going super fast or things that are super, super big. Does that make sense? Things that are going super fast or things that have a lot of energy. I think that's what it is. So Einstein figured out that if you're going very fast, you're moving through space-time, and the way that your personal time ticks is different to other observers that are not moving at that speed. We're not going to get into this too deep. I'm very excited to actually talk about that on the channel. But it is a crazy subject because you need a lot of vector calculus as well. And you need 4 vectors because you're describing 3 positions of space and 1 position of time. So you create a 4 vector. And you use this thing called Einstein notation. Very cool subject. And I actually did some videos on this as well. It's some cool stuff comes out of it, like time dilation, length contraction, relativity of simultaneity. So if you're far from somebody, you cannot say anything about the moment now. So Newton back in the day thought that time was the same everywhere, and everywhere is now, and then everywhere at the same time elapses in time. So somebody in Europe and somebody in Andromeda Galaxy, they're experiencing now, and then they tick forward 1 second per second as time moves on. But we figured out that's not the case. Time is relative to where you are, which is super crazy. It kind of puts you at the center of the universe, the observer. Which is another cool thing about quantum mechanics. It's related to observers because there's the collapse of the wave function. Anyway, we got classical mechanics, E&M and electronics, thermodynamics, quantum mechanics, relativity. We got solid state physics, which is the study of objects, which uses some quantum mechanics, and statistical physics. So statistical physics, I would just say, is just a bunch of stats. I was never really that good at it, but I think we should do that on this channel as well. We got some crazy theories that merge quantum mechanics and relativity together to get quantum field theory. Also very, very cool and very modern. Quantum field theory started getting popular after the 50s, 60s, 70s, maybe 80s. 1980s, I mean. But recently it's gone kind of stagnant, I would say. I'm not reading up about this too much. But yeah, I think I've hit all the subjects here. So those are all the physics classes I've taken. Along these, you also take a lot of math classes. You got to learn about calculus, you got to learn about linear algebra, you got to learn about differential equations, partial and full or ordinary differential equations, and statistics. You got to learn about a ton of math. But the cool thing about studying physics is you don't have to learn math so foundationally. When you learn math, for me personally, I think it's so hard to grasp. But when I'm applying it to some problem, like a physics problem, it kind of roots it in reality a bit. So learning math from the physics side of things is pretty cool. I like it. But I would also like in the future to have some foundational math classes like proofs, like set and group theory, crazy shit like this. So math is a big, beautiful field. The more math you learn, the more beautiful it gets. The more physics you learn, the more beautiful it gets too. But the more you learn, the less you actually realize you know. So I'm just sharing this, a little bit of a journal for the gang here, a little bit of a diary, so I can one day look back at it and be like, yo, this is what I knew. I didn't know that much, and now I know even less. So I hope you guys enjoyed. Let me know if you guys want to see anything in the next year or so on this channel. Typically what I'm doing, maybe it's not the best, maybe it's a little boring, but I'm reading the textbooks. I think reading the textbooks is important. I'm basically going through this shit word for word, and I'm not doing so many problems for quantum mechanics, but doing problems is also important. I just don't want to do a problem and then make a ton of mistakes and then make the video like 7 hours long. But maybe that's what it has to be. So I've been trying to solve the problems on my own time and then summarize the problem on a video. Maybe I'll do that in the near future for quantum mechanics. And yeah, thank you guys for watching. Thank you guys for subscribing and liking the videos and commenting. This is a great community of physics lovers. And I will see you guys in the next video. Peace.